I will talk about this joint work with Orbirn-Zweig and Eli Porat. So I will first define the two problems that we will consider in the paper, and then I will talk about the actual several highly overview of the result. So the first problem is the longest common extension problem, which is a data structure problem. So we are given some string S, and we want to be able to support queries of given pairs of indices I and j. We want to compute the longest common expansion, which is the longest substring, shared substring that started at positions I and j. So for example, here, the longest common extension is 5. And as probably many of you already know, there is a classic solution uses suffix trees. And just to remember, to recall, suffix tree is the compact trie of all the suffixes of a given string. So it is well known from the 80s that one can use can build a suffix tree in linear time and add an LCA, which is lowest common ancestor data structure on this tree. The whole construction time and space usage is linear, and then the LCA queries can be solved in constant time. So it's kind of optimal data structure. However, we consider the problem in the settings of small space, where we assume that S is given in read-only memory. It's not compressed, but it is read-only, and we have a space limitation on our data structure and even on the working space. So the space we can use is just n over some parameter tau, and there is a lower bound of omega tau query time when we are limited in our space, which was proved by Kosolobov for small values of tau, and its conjecture for any value of tau. So what are the results for this problem? So if we want a randomized Monte Carlo algorithm, then the previous result, which actually solve the problem for these settings, is by Tomasz and Pavel, and they get everything as good as it could be. So the space is n over tau, as we said. The query time is order of tau, which we assume it's optimal, and the construction time is linear. However, if you want Las Vegas algorithm, then the result have additional factor in the construction time is slightly worse. It takes n times square root of log n over tau. And we introduce here a result that have linear expected construction time and even linear with high probability, as long as tau is not too large. And in the deterministic regime, the previous best result was by Tanimura et al. They have additional factor in the query time of minimum between log tau and log n over tau. So for tau, which is some small constant polynomial in n, it is tau times log n. And also their construction time is not so good, is n times tau. We improved the construction time to n log tau, and our query time is almost optimal, is just off by a factor of square root of log star n. However, new result that was uploaded to arXiv last year by Kosolobov and Sivukhin uses our technique and improve the result to be actually with optimal query time of tau and order of tau, and construction time, which is almost linear. It's n times log n based n over tau, which for tau, which is again a polynomial in n, it will be just linear time. And I will talk shortly at the end about their improvement. The other problem that we show how to solve, it's the two problems are closely related. So it's a generalization of the suffix tree construction problem. So if in the suffix tree construction we are given a string and have to build the compact trie of all its suffixes, then in this version we are given also a subset of the suffixes, subset of positions, and we have to build the suffix tree just of the suffixes in the set B. And it is well known. It is pretty simple to build such a sparse suffix tree just by building the complete suffix tree and prune the suffixes that are not in B. However, if we have limited working space, then the problem is not so simple. And so again, we assume the same model that the string is given in read-only memory, and we have just our space is linear in the output size, in the size of the work of the sparse suffix tree. And for this problem, we introduce randomized Las Vegas algorithm, which is optimal as long as B is not too small. And for deterministic algorithm, we have additional factor. So the running time is the order of n times log n over the size of the set, n over b. So I want to start with, I will focus on the result on LCE data structure, and I want to give the idea. So the first observation, useful observation here, is that let's think about the case where we don't have any time to preprocess. Let's think about it as just a algorithmic problem, not data structure. So if we didn't perform any preprocessing, then when we are given the string and the two indices, we must just compare the synchronized position, which means we compare Si and Sj, and if they are equal, then we compare Si plus 1 and Sj plus 1 until we find a mismatch. So of course, the running time of this algorithm is linear in the LCE itself. So since we know that there is a lower bound of order of tau time, then for pairs of indices I and j, where the LCE of I and j is small, is order of tau, then we don't need actually to do any preprocess, and we can just solve the problem naively when we get the query. And therefore, we have to focus on pairs of indices I and j where they have a very large LCE, which is larger than our parameter tau, and therefore we can assume that we are only considering cases where the same string appear at least twice as a substring in the text, and it is a large string. It is at least of length order of tau, and to solve this kind of issue, we introduced the notion of tau partitioning set. So the tau partitioning set is a set of positions from our string between 1 to n that have three properties. The first property is that the size of the set should be small to fit our memory, to be order of n over tau. In addition, we want it to be local consistency. So as we said, we only considering the case where we have a large string that appears more than one, and then we want that the same location or appropriate location will be taken into the set P in all the copies of the set, and therefore we want local consistency, which means that if the decision whether a specific position I is in the set or not depends only on short string around position I, here of length 4 tau around position I. And we also want that this set will be compact, which means that if you consider the points in the set as beginning of blocks, so each block is between 1 point to the successor point, then we want that the size of each block will be bounded by our parameter tau. The problem is that we actually cannot get all these three properties as they are written now in all cases. For example, in the case where the string is composed of a repetition of the same string, then due to the local consistency property, we know that either almost all the positions are in the set, or none of them, because for all the positions, except for the boundaries of length order of tau, the local string is the same, and therefore the decision must be the same. However, due to the compactness property, we probably have to choose to consider all the positions because otherwise we have large gap between positions or just one block, but then we have too many points. Therefore, we have to define a little bit more detailed definition, and we allow large block, just in cases similar to this case where the large block has a small period, smaller than order of tau. And for the sake of simplicity now, let's just focus on the case where we don't have such cases. Let's think about square-free strings, which are strings without any repetition in them. So for these strings, there are tau partitioning sets, and we describe in the paper how to find such sets, and I will talk a little bit about it in a minute. So now I want to describe why it's good to have a partitioning set and how we can use them to build an LCE data structure. So the idea is that, as I said, we can consider the points of the partitioning set as endpoints of blocks. So here, for example, if these are the partitioning set, then the points in the partitioning set, then these are the block, and we can consider we can sort all the blocks, the substrings that are the blocks. If we sort them, we can find the duplication. So, for example, as you can see here, the block numbered 2 appears twice, and therefore, after the sorting, we can identify it and give the 2 copies of the block the same name, the same label. And now, if we have, as I said, a long string that appear more than 1, then it will be partitioned into block in a very similar way, in almost the same way, except for the margins of this long substring. And therefore, if we now consider each block as a character, since the number of blocks is the number of positions of the partitioning set, which is order n over tau, we can build on this short string an LCA data structure just a standard, as I said earlier, by suffix tree and LCA. As I said, it's optimal if we have the space, and for S prime we have such a space. And now, when we want to answer LCE query, the observation is that if the LCE of 2 indices is large, is more than 5 tau, then it must be the case the string, the 2 copies of the strings are composed of the same blocks, as I say, because when I look on every point in the shared string except for its margins, they see a similar string, and therefore the decision is the same, and therefore they are composed into same blocks. And now, when we want to compute the LCE, we can compare on order of tau pairs of characters. If we find a mismatch, then great, we know actually exactly what is the LCE. And if we, let's say, read more than 5 tau pairs of characters, then we can stop, and we know that we find synchronized position somewhere in this 5 tau indices, which means that it's the same L prime, such that I plus L prime and J plus L prime are both positions in P. So it's we have blocks starting at similar positions in corresponding positions in both the region after I and the region after J. Then we can compute the LCE of the blocks, which give us the position of the last block, where the last block that is shared between these 2 regions is ended. And soon after the end of the shared block, it must be the case that we will find a mismatch, because otherwise the blocks should still be the same, and we know that they are not the same anymore. And therefore, the total query time is order of tau, and that's what we actually want. So in the paper, we introduced a randomized construction of partitioning set, but now I want to focus on the deterministic construction. However, our deterministic construction is slightly worse. Instead of having local consistency property that the position I depends only on a string of size order of tau around it, it depends on string of size order of tau times log tau n, which is not so good. It's slightly worse. However, it was, as I said, recently fixed by Kosolobov and Sivukhin that actually introduced a way to choose partitioning set with order of tau local consistency, and I will explain it at the end of this talk. So the basic idea for our deterministic construction is going back to the 80s. It's going back to the technique of deterministic coin tossing that was introduced by Kolan and Sivukhin. So the idea here is to have a method to change the alphabet of a given string, to convert a given string of general alphabet, polynomial large alphabet, to S prime of constant alphabet. It will be of size 6, that have the property that if we have two adjacent characters, let's say here C and B, which are not the same, then also in the new string S prime, the new labels of these characters will be also different. And notice it is not mapping, so it can be the case that in one position B will be translated mapped to 2 and in another place to 4, but it is has the local consistency property. That means that if we have a large string that appear more than once in the string, then it will be mapped. All of this string, except for maybe small margins of the string, will be translated exactly the same to the constant alphabet. And I want to describe how this alphabet reduction works. So we look on our input in its binary encoding, and for any position I, if this is the encoding of Si, then we consider, we are looking at the encoding of Si and the encoding of Si plus 1, and we are looking for the least significant bit, the first bit from right, that the two strings are not the same, are different. In this case, it's the bit at index 6. And then we define two parameters. One is psi, which is the position, the index of this mismatch, this different bit between the two adjacent characters, and the bit which is in this position, what is the bit of the of Si, of the left element here. And our new label will be the concatenation of psi and the bit, psi, of course, in binary encoding. So, for example, 6 here is 110, followed by the 6th bit of Si, and we are doing the same here. So now the first mismatch is in position 3, at index 3, and the bit is 0, and so on and so forth. And what Kolan and Sivukhin show is that using this process, it is guaranteed that, as we said, that if the two adjacent characters were different originally, then their new labels are also different, because there are two options. If the psi, the position where Si is different than Si plus 1, is different than the psi of I plus 1, which is where Si plus 1 is different from Si plus 2, then of course the encoding will be different. And even in the case like here, as you can see, the last two labels here are the same. Their psi is the same. They have the same position of mismatch, but then the actual bit that we concatenate to the psi is the actual bit of each one of them, which by definition is different, because this is how we define psi, and therefore we get the desired property that if the original string was different, then also the string after the alphabet reduction is different. And now this was just one iteration. We can repeat these iterations again and again to get smaller labels. And if we started with labels of length x, then in any iteration, we reduce the size of the length from x to log of x to the representation of psi plus 1 for the bit, which is logarithmic decreasing in the length size, and therefore in the length of the label, and therefore after order of log star n iterations, we will be in with constant size, which will be in this case, one of 6 elements. And as you can see, at every iteration, our dependency is just with additional adjacent character, and therefore after log star n, order of log star n iterations, the dependency will be just on log star n elements. And now we can use this technique to split the string into blocks. We choose the local minimas. Since we have constant alphabet, then we know that the local minimas are not too close. There is at least distance of 2 between any 2 local minimas. There are no adjacent local minima, but the maximum distance is also bounded by constant. In this case, it's 11, but it's not really important, the exact constant. And we now can consider each block as a new character, and applying this technique again for this for the new blocks. The original the first usage of this technique by Sahinalp and Vishkin was in different settings, and they just used the observation that there are at most, since the distance between any 2 adjacent local minima between two local minima is at least 2, then the new number of blocks is at most half of the original, and therefore if we repeat this process log n times, then order of log n times, then we get hierarchic decomposition of the text. However, for our case, it's not good enough. Why is it? Because it could be the case that in the same level, let's say in level 2, there are 2 blocks with really different length. Why is it? Because due to the difference, as we say, each block is composed of something between 2 and 11 blocks. It could be the case that in some level we have a block of size 2 to the mu, level mu, and another block of length 11 to the mu, which is for large mu. It is a really different length, and it is not what we want, because we want that almost all our blocks will be of size order of tau. And therefore it is not good enough. So what we suggest is that at any level, our goal is to have blocks of length 2 to the mu. And if we get a block which is already of size above 2 to the mu, then we don't have to change it. We can keep it as it was in the previous level. And we actually get not that all the blocks are of the same size. It could be the case that there is a block which is really small, but we get that we have our number of blocks is bounded by n over 2 to the mu, and the maximum size is order 2 to the mu. You can think about it as the average size of a block and the maximum size of the block is roughly the same, up to some constant factor, and then we just assign look at level mu equals log of tau, which gives us that the size of each block is bounded by tau as we want, and we have n over tau blocks, that which is what we have, how much space we have, and now each position, if we think about the last level, is composed of, it depends on log star n characters in the previous level, but the characters in the previous levels are blocks of length order of tau, and therefore each position depends on tau times log star n characters, which is almost what we want, but not exactly the same. And the time here, the construction time here is n times log tau. There is some calculation there in the paper, which is not so important now. In the last few minutes, I want to just give a high overview on the new result of Kosolobov and Sivukhin. So they followed our technique with, of course, some different details, but in the high level, it's similar technique, and they just using slightly a different level. They choose the level tau over log star n, log of tau over log star n, which is where we have slightly more positions. So the length of each block now is smaller, and therefore it depends on less characters, which is actually what we want. However, of course, there is the cost, which is that the number of positions in the set is too much, and we don't have enough space to store all these positions. So it is off by factor of log star n. And then they show how to solve it by, instead of storing all these positions, they create a corresponding string in some specific way. So the idea is that since they not save the actual positions, but just a little string for any position, then using bitpacking technique, they can store in n over tau words in the memory. They can store n over tau times log squared n, log star n information, or information about n over tau log star n positions where the information is small enough. And then they use technique of Yesh of recompression to sparsify the string R with a specific way to make sure that it's both stay local consistent and valid, which means that they don't remove too many positions and create too large gaps. And then, since of course the string R cannot store all the information about the positions because it not have enough space, but they use the fact that the string is given, the original string is given in read-only memory. So they actually can rerun all the algorithm from the beginning, but now instead of storing all the positions, don't have space for it, they store just the positions that survive the sparsification that made by the recompression process. And this is how they get just n over tau positions with dependency of tau. So to summary, we introduce the notion of partitioning set. I don't talk about it now, but in the paper you can find the randomized construction, which is optimal, Las Vegas. And I talked about the deterministic construction with the improvement of Kosolobov and Sivukhin. And this is useful, as I said, to build an LCA data structure, as I explained, and also for sparse suffix deconstruction. And that's it.